Welcome back from lunch. Hope you chewed slowly. Hope you don't get indigestion. Hey, speaking of, have you seen those awesome new Pepto-Bismol commercials? Upset stomach, diarrhea, whatever. Indigestion, heartburn, upset stomach, diarrhea. Yeah. I mean, it's like weird, like singing like a jingle to like diarrhea, you know? Anyway, because when you were in second grade, that was a joke. Like, right, when you're sliding into third and you squeeze a big turd, diarrhea. You never? No? Okay, never mind. I grew up in the valley, so I guess that's what we did. When you're sliding into first and you feel a big burst. Why are you sliding into first? Just run through, okay? All right, anyway. No? Just me? Okay. This is recording. I forgot. Oops. Letter E. Okay. I'm sorry. The endpoints are not going to be local extrema because they're not on open intervals. Will F of C be a local max or min? Will that be a local max or min? Yes. To the left it's higher, to the right it's higher. So good. That's a local min. Ugh. I wish I knew how to edit video. I don't. Okay. Because I'm from the 90s. Do we have a local max or min here? Left lower, right lower. Yes, indeed, we have a local max. Good. How about this feller? Local min. Okay, so for continuous functions, it's real easy. If you have a hill, any hill, it's going to be a local max. If you have any valley, it's going to be a local min, even if it's a cusp valley, right? Good. Any questions on that? Moving right along then. Number 5. Let's do the critical values from -4 to 4. From -4 to 4. We'll just say CV's at X equals. We'll go from left to right. Where's our first critical value? Hello, Greenwell. Did you know that the Mac Dad will make you jump? And Daddy Mac will make you jump. That's why they were so successful as a crisscross duo. They both made you jump. Yeah, one of them's dead now. And one, that's right. And that's enough to make you jump, right? That's all you need. Well said. All right. What's our first critical value from left to right? -4. It's an endpoint. The derivative is 0. It's in the domain. Where's our next critical value from left to right? Is it at -3.5? -3. Oh, yeah, cool. It's a hole there, but notice the dot is defined up there. So it's in the domain and the derivative is undefined. Well done. Okay, adios, Greenwell. Where's the next critical value? Is it at -2? That's not a critical value, right? That's just an x-intercept of the function. The derivative is not 0 there. Okay, where's the next one? -1. Good. The function's defined there. It's that dot, and it's discontinuous, so the derivative doesn't exist. Where are the next critical value? 1 would definitely be a critical value. What about all of the values between -1 and 1? Yeah, when you got that horizontal line, it's kind of like, oh, really? Okay, all right. So then we're going to say all the values on the open interval from -1 to 1. But those, we're not really interested in those. Those are kind of like cheating kind of critical values. What about at 1? Is that a critical value? Yes, only because the function is defined there. Again, if that open circle or if that solid dot had been gone and there was an open circle everywhere, it wouldn't be in the domain. It would not be a critical value. Still an interesting value, but not critical. Where's the next one? 2. Yep. What about 3? Nope. What about 4? Yeah. Okay, good. So those are the critical values. Now let's go through at each of those and say local max, local min, or neither. For local max, I guess we'll put LM. For local min, we'll put LM. No, that won't work. Okay. We'll put N for neither. How about that? Here at -4, is this blue dot a local max, local min, or neither? Neither. Yeah. Now, a little bit about this. If you go to college and you get a professor and he says, I'm going to call that a local min and so should you, you're going to be like, okay, you're the one grading my papers, I'm going to call that a local min. There are some schools of thought that allow local extremists to live on cul-de-sacs, okay, dead-end streets. But not me, not College Board. We have to live on an open interval. I could see their argument, right? In that local vicinity, that is the lowest point. But it doesn't live on a through street. So we disqualify it, but You might meet someone in your life who insists that's a local min. Just acquiesce and move along, okay? Don't start tweet raging about it or anything. Okay, what about -3? Local max, min, or neither? Rage tweeting, not tweet raging. Sorry, that's okay. God, I'm embarrassed. Neither? Well, let's see. We go to the function value, which is way up here at 1. Immediately to the left, immediately to the right, we have values on both sides that are what? Lower. So that is going to be a local max. Okay. Hey, that reminds me. Anyone here ever climbed Mount Everest? There is a part of Mount Everest. It's a traverse right before you get to what's called the Hillary Step, which is like a 30-foot vertical climb of ice near the top. There's a traverse that you have to make. It's a dangerous spine, and it's kind of nerve-wracking. Okay, on one side, let's say that this is we'll look at it from this perspective. We'll say that this would be the spine. This would be the south side. This would be the north side. Okay, on the south, of course, is what country? If y'all know y'all's Himalayan geography. Tibet is in the north. Good. Tibet is in the north. And then in the south we have, well, that's a little further south. Yeah. Where are the Sherpas from? Nepal. Yeah, good. All right. So they're on the spine, on that little spine where you're traversing over to get to the Hillary Step. If you slip and fall into Nepal, it's about a 5,000-foot drop. I put 5 foot. 5 foot. It's a 5,000-foot drop. If you fall into the north side, into Tibet, it's about 7,500-ish, 7,500 feet, okay, into Tibet. So it's a longer fall in Tibet. So the wisdom goes for anybody climbing Everest, I've looked into it, is if you're going to fall, you should fall onto the Tibetan side. That way, you'll live longer. That's a long way to go for that. Okay, so why am I reminded about that? Because notice, if you look to the left, you fall a little farther on that side than you fall on this side. It just came to my mind, so I just thought about it. But anyway, yeah. Fall to the Tibetan side, so you'll live longer. Huh? Fall to the northern side because it's a longer. Oh yeah, it's reversed on the graph. I should have drawn it backwards. Yeah, the graph is backwards from my example. Yeah. So if you're like on this, if you're like standing here, hey, look at me, I want to be on Jackass. Is that the show? Yeah. Right. Look at me. I'm on one of those little scooter things up here, right? Those little hoverboards. Hey, right? If you're going to die, fall on this side. You'll live longer. Okay. Again, this is recording. Okay. Is -1 a local max, min, or neither? That one's a neither, because you go to the function value. You don't just go to like an open circle. To the left, it's lower, and to the right, it's higher. Right? So that's a neither. Okay, what about all of these cheater values between -1 and 1? Very good. For the same argument we did with absolute extrema, these are all local maximums and local mins. I tend to use local instead of relative. If you look left and right, there are no values that are higher, so they're local maximums. If you look left and right, there's no values that are lower, so they're local mins. Okay? So the horizontal line case is just kind of like you're cheating kind of case. All right, what about at x equals 1? Local max, min, or neither? Local min. You go to the y value, to the right there's higher, and to the left there's higher. Okay? So obviously, local extrema can also occur at discontinuities. What about at 2? Local max, min, or neither? If I look to the left, there's lower, and if I look to the right, there's lower. Is that how that works? No. You have to look immediately to the left and right. In other words, if there exists an open interval, if you want to do that, these are parentheses. If there exists an open interval containing it such that on that interval, it's the lowest point, it's a min. Not if you can find one, if there exists. So that's why I say, if you look immediately to the left, higher, immediately to the right, higher, right? And now this guy looks like, I give up, right? I don't know. I guess he's shrugging his shoulders. That's why it looks like his arms are coming out of the side of his head. I give up. He's hanging on, right? So this would be a local what? Min. It's a local min. Absolutely. All right, what about at Fjord? Look, if you zoom in that local region, it's like, hi. Nothing. Good. It's a neither because it's an endpoint. Good. You getting the hang of it? You can have several local extremos, just like you could have several local officials, right? But only one global. If it exists, only one absolute. Min, max, if they exist. Okay. Example 6. Kind of moving away from graphical to kind of analytical. Find the domain and the critical values of each of the following functions. Why would I ask you to find the domain before I ask you to find the critical values? Because critical values have to be in the domain. And if you just get into a comfortable pattern of saying, I want to find out where the derivative is 0 or undefined, you may be calling something that's not even in the domain of the function a critical value. Because remember, if it's not in the domain of the function, it will not be in the domain of the derivative. So you got to be careful. All right. Letter A. What type of function is this? What's the domain? All real numbers because it's a polynomial. Polynomial. Very good. So the polynomials are not only continuous everywhere, they are differentiable everywhere. So the domain of F is all real numbers. Now we want to find the critical values. How do we find the critical values? Yeah, take the derivative and see where it's 0 or doesn't exist, okay? So let's take the derivative first. First things first. F prime of x is 4 times a half is 2, so we get 2x cubed minus 3x squared minus 2x. 2x, sorry. 2x. Worst fest. Now, we're going to use this twice. Guess which of the two cases most students tend to forget about and overlook? The DNE or the 0? The DNE. Most students are like, take the derivative, set it equal to 0. Take the derivative, set it equal to 0. And they forget about DNE. So that's the one we're always going to do first. We're always going to do it first so we don't forget about it. We consider it. Always consider it. Is that cubic polynomial, that is f prime, ever undefined? No. So we'll just say there's no solution. Now, you don't have to physically write it down like that, but I want you to at least think about it. Is that polynomial ever undefined? It's not. Okay, we thought about it. There's no solution. It's not like we forgot to even consider it, and so we didn't write anything down. And now we want to know where it's equal to 0. So if you just set f prime equal to 0 for a problem like this, you're going to get a check. You'll get a check for the derivative, and you'll get a check for setting it equal to 0. So that goes for any time you're setting up an equation. Show the equation you're solving. All right, so what's the first rule of factoring? Panic? Yeah, and then when that subsides, look for a common factor. Aside from a -1 or a 1, we have an x, right? So I'll get x times 2x squared minus 3x minus 2, and I'll keep it equal to 0. That's the important thing as well. Once you set it equal to 0, you got to keep it equal to 0 as you work down, because if you leave it off on one of the lines, you could lose points. Well, you can split it up now and say x equals 0 and the quadratic equals 0, or let's just go ahead and see if we can factor the whole thing before we split it up. So this is the fun type. It's a quadratic trinomial. The leading coefficient is 2x squared, so it's going to be a 2x and an x. The constant is 2, so it's prime. So it's either got to be a 1-2 or a 2-1 combo. It's probably going to be a 1-2 combo, and then a negative and a positive, and then you can check. So whatever method you use for factoring, we still need to be able to do that. And now, instead of setting each of them equal to 0, at this level, BC, you should be able to look at that and just rattle off all three solutions. Did I do it wrong? -4 plus 1. Okay, yeah. I thought I checked mentally, but I did it quickly. And I'm also thinking about Wurstfest, which the German club gets to go mañana. Später? Im Morgan. Im Morgan, yeah. Okay, x equals, this one is 0. This one is what? Negative 1/2. Good. And then this one is 2. So those are your 3 critical values. Okay. Now, it should be no surprise to you that a 4th degree polynomial can have up to 3 critical values, right? Because a 4th degree polynomial might look something like this. Okay, and it can have not only 3 critical values, but it could have 3 local extrema. That 4th degree polynomial, though, doesn't have to have 3 extrema. It could do something like this. This would be a critical value, and here's a horizontal tangent that's actually not a critical value. But a case like that would only have how many critical values? It would only have 2. It's impossible to draw that with the third one. And so having 3 critical values, actually, if you know something, you know it's going to look something like that. So without even doing any tests, just with your knowledge of polynomials, do we know the location of that first local min? Yeah, it's got to be one of those 3 values, so that should be negative 1/2, right? That's the smallest. This local max should be at x equals 0, and that local min should be at x equals 2. Now, there's another way that we're going to use to figure that out later on, but I'm just saying if you bring in everything you've learned up to now, you can use it, right? It's all good. Okay, letter B. We got g of x equals that. What's the domain of this function? All real numbers. Good. We're trying to avoid division by 0. We don't have any variables in the denominator or to the negative exponent power. We're trying to avoid even roots of negatives. We don't have any 4th root square roots or fractional exponents. And we're trying to avoid logs of anything but positives. We don't have logs. Unless it's a piecewise function, which this one is in disguise, it's all real numbers. But we know what this function's parent is, right? This is your V for victory graph. How do we find the critical values of this guy? Can we take the derivative? We could try. We've actually done one like this. You would have to use the identity square root of x minus 4 squared, and you'd have to use the chain rule. Or you would have to split this up into a piecewise function based upon the sign of x minus 4 and take a piecewise derivative. Yucky, yucky, gross, gross. How about this? What do we know about any linear absolute value function? It's going to have a critical value at the location of the what? Yeah, where the sharp turn is, which is at the vertex, right? Remember how I told you earlier how to find the vertex quickly? You take your argument, which is what you're taking the absolute value of, and you set it equal to 0. What value makes that 0? 4. So for these types of functions, we'll just say critical value at x equals 4. You can actually graph it. It opens down, and it's moved right 4 up 2. Okay? So keep that in mind. We don't want to really have to take the derivative of those types of equations. We could. There's 2 ways, but it's very labor intensive. Almost takes the fun out of it. All right. Letter C. F of x equals that. We have 2 factors. What's the domain of this function? We have a fractional exponent, so we do have to be careful. But that's the same thing as the 5th root of x cubed. Is it okay to have negatives under a 5th root? Yes. So if that were a 4th root or a square root, we'd have to avoid negatives. So that's the only thing that might cause us something to break when we plug it in. It passes that litmus test, so it must be all real numbers. The domain is all real numbers. Now, how am I going to find my critical values? I need the big D, not Dallas. Oh, my gosh, Dallas, what are you doing? Getting doubled last night. It's been broken since the late 90s. Okay, f prime of x. We need the derivative, right? What rule are we going to use here? The product rule. Okay, so the derivative of the first is 3/5 times x to the negative 2/5 times 4 minus x gets rewritten. Plus x to the 3/5 gets rewritten times the derivative of 4 minus x, which is negative 1. Now, later on, we're going to be factoring out least powers, unless you want to do it now. No? No? Okay. So you could just simplify each term. That's going to be a 3 in the top and 5 in the bottom. That x to the negative 2/5 goes to the bottom now as the 5th root of x squared. And then we're left with the 4 minus x in the top. And then this one becomes minus, we'll call it the 5th root of x cubed. All right, so how are we going to determine then where the function f is got critical values? We want to know where this thing equals 0 or is undefined. Actually, in order to set it equal to 0, I want it to be a single function. So if we didn't factor out least powers, what we're going to have to do now is get a what? Common denominator. And bless you, and in this case it's easy. I'll just multiply by 5 5th root of x squared over 5 5th root of x squared. So now I'm going to have the denominator as 5 5th root of x squared, and the top, I'll go ahead and distribute. I get 12 minus 3x minus 5 times 5, 25. And now that's going to be x to the what power? Oh, it's not 25, my bad. That's, you got to be careful. That little root index looks like a 5 out front. It's not. So it's minus, that's really x. Let's come up here. I should have maybe left that in rational. That's x to the 3/5 times x to the 2/5. So we just got the 1/5. What is 3/5 plus 2/5? X. Yeah. Okay, and now I can combine those, and I get 12 minus 8x all over 5 times the 5th root of x squared. And I can even go further. I could factor out a 4, and that gives me 3 minus 2x all over 5 5th root of x squared. So this is kind of the holy grail. This is what we work really hard for. We want to get what I call a full-fledged factored version of f prime. Full-fledged factored means all of the derivative parts are still there. It's a single term, and it's factored. Okay? The reason we want to do that is because now it makes finding critical values a snap, if you know how to snap. Some people don't know how to snap. Like, that's not easy for me. Okay, there you go. All right, here's why. Which one do we consider first, D and E or 0? Let's get in the habit of doing D and E. Now that it's a single fraction, a fraction is undefined when the what's 0? Denominator. You don't have to even worry about the 5. If you want to put the 5 there, that's fine. 5 5th root of x squared, set it equal to 0. What value of x makes that 0? 0. Okay? Now, you got to be careful. It's not in the domain of f prime. Is it in the domain of f? Yeah, we said the domain of f was all real numbers. So is it a critical value? Yes, it is. Now, because it only makes the denominator 0, that's going to be a vertical tangent. Or it could be a cusp with a vertical tangent. So it could be like this. It comes in vertically and goes back out. Comes in vertically, goes back out. It could look like this, or it could look like this. Okay, it could be any one of those 4 types of things. Because in each of those 4, the function exists, but the derivative doesn't. Okay? Now, over here, down this other fork, we'll say f prime equals 0. Well, now that it's a single fraction, that's going to be when the numerator is 0. So we'll take the numerator and we'll set it equal to 0. And, of course, you could divide by 4. So what value makes 3 minus 2x 0 when you plug it in? 3/2. Okay? Now, that only makes the numerator 0, so that's going to be a horizontal tangent. So that's going to end up being either a local max location, a local min, or it could be like x cubed where it does that, or negative x cubed where it does that. It's going to be one of those 4 things. So those are the 2 critical values. Now, right now we're just finding critical values. We're not deciding if they're local max or mins, but we're working up to that. So right away I can ask you this question. Is every critical value going to be a local max or min? No. But they are potential. It's the only place where a local max or min can occur, is at a critical value on the interior. But not every one of them is, right? So like if we looked at the one on the left, only in 2 of those 4 situations is it a local extrema. If we look at the one on the right, only 2 of those 4 situations is it a local extrema? Okay? So anyway, we have that. Any questions on finding? Oh, I know one last point I want to make. How was it that the derivative was undefined at 0, but the function wasn't? Well, let's trace the steps backwards. It was because we got a 0 in the denominator because there was an x in the denominator. How did the x in the denominator get there? Well, it was there because we had a negative exponent, right, on the x. How did we get a negative exponent on the x? We started with the positive exponent that was 3/5. 3/5 was less than 1 and greater than 0. What's going to happen anytime you use the power rule on an exponent that's between 0 and 1? It's going to end up being negative. So anytime you have a fractional exponent less than 1, you need to be on red flag alert that I'm going to call cusp alert, cusp alert, cusp alert, cusp alert. Or you can also add in there vert alert, but that doesn't have a list. It's not as fun. Okay, cusp alert, cusp alert. Now, not only are you going to be on cusp alert, but if you look at the root of the base of that exponent, you will know the x value that will be a critical value and a cusp. The base of that exponent is x. What value of x, when you plug it in there, gives you 0? 0. Is that not where we had our vertical tangent? Yes. So, there you go. Anytime you have a fractional exponent less than 1, but still positive, you're going to be on cusp alert, and you're going to be able to find that x value too before you proceed. All right, we will stop right